Okay, so I'm going to get myself into trouble, and I am going to prove something to you without defining a lot of objects, so you guys can get a feel for what is going to happen. So, so here's a theorem. Okay, so I'm going to prove that the third homotopy group of the two-sphere at infinity, so the dimension of this is bigger than that, this is going to be isomorphic to the free group on one generator. Okay? So, and I want to make sense of all of this. So let me say what we're going to do. Okay, so let me just give the proof. Okay, so here's the proof. Okay, so so what we do, what we're going to use is to do this is we're going to use some vanishing results. We're going to use let me just say. Okay, so we're going to use kind of a short exact sequence. So we have a short exact sequence of topological spaces. Okay, so this is actually a fiber bundle, but we have S1 includes into S3. So these are all spheres. And this goes on to S2. Okay? So, okay, so in anytime we have one of these special fiber sequences, so this is what will be called a fiber sequence. Okay? So we get we get a long exact sequence of these pi's. All these pi's fit together. These higher homotopy groups. Okay, and so so we can go down from the bottom, and so we'll have pi 1 of okay. And so let's take them pointed at infinity. So we're reviewing them as like a compactification of R2 plus a point at infinity. Okay, so then we have pi 1 S3 infinity. And we have pi 1 S1 infinity. Okay, this keeps going. And what happens is, okay, so then we're going to have, here's the long exact sequence. S2, pi 2 S3, pi 2 S1. Okay, pi 3 S1, pi 3 S3, pi 3 S2. Okay, so we have a bunch of groups like so. And we're going to get a long exact sequence like this. Okay, so a long exact sequence means that the image of one is the kernel of the next. All the groups, all these higher homotopy groups for any space, they're going to be abelian except for, in the case of n is equal to 1, for any space. Okay? I mean, in some cases, it'll still be abelian, but pi 1 will still be abelian. But we will always have that pi n for n bigger than or equal to 2 is an abelian group. Okay, so what we're interested in was computing this one of the two spheres. So we have this, whatever the short exact sequence is. This is called the Hopf vibration. So what are we going to, what's going to happen? So we want pi 3 of S2. So pi 3 of S2 is here. Okay, that's this one. And we have pi 3 of S3. Okay, so it'll turn out that pi 3, and then, okay, it'll turn out that this one goes away, right? So pi, I need to be able to prove things like this. Pi 3 of S infinity is equal to, is the identity, okay? And then the other thing is I'll want pi 2, right? I also want this to be the same thing as pi 2. Pi 2 S1 infinity. This is going to be the identity. And then we're also going to need that pi 3 of S3 infinity. So this is going to be infinite cyclic. Okay? In general, this will be for pi n of Sn. So that's what we're going to do. Okay? And then, so these, it turns out that when you're only focusing on something, you only need, so again, we're zoomed into this piece here. when you have a long exact sequence, you don't really need all this extra information. This actually goes up even more, right, if we wanted to continue. But we're not going to use that. We're just going to use this piece. And so since this is isomorphic to Z, and it's surrounded by two ones, right, in an exact sequence, it means that this is an isomorphism. So maybe I can prove that lemma since it's always going to be appearing all the time. But I mean, that's essentially the proof, but we're really applying a lemma. Okay, that says that, and maybe you haven't seen these exact sequences before, but I'll repeat this in the definition so that if we have an exact sequence like this of groups, G1, so we have alpha, beta, G2, gamma, 1, is exact, right, at G1 and G2, then a G1 is isomorphic to G2. Okay, so here's the proof. So by exactness, what does exactness means? So exactness means that so it says two things. It says that the image of alpha is the kernel of beta, and that the image of beta is the kernel of gamma. Okay, so the kernel of gamma, so I'm going to prove that it's injective and surjective, this map beta. Okay, so this one here is 1. So the kernel of beta is 1. So this thing gives us injectivity. Okay, and then the image of beta is the kernel of gamma. This thing is the whole. This is the whole deal. So this is all of G2. So this tells us that the image of B2 is all of G2. So this implies surjectivity. A surjectivity of beta. Okay, and so since you have injectivity and surjectivity of a group homomorphism, this is a group isomorphism. Okay, so this is our first long exact sequence using this fibration. So this is a fiber bundle. This is an S1 bundle, and then we use some vanishing stuff here. And so this result here, I'll just say this real quick, is that this has to do with the universal cover. Okay, so all right, I'm going to stop there and kind of try and define all these things now.